With this short introductory note, I hand over the session to Dr. Giri Babu. The stage is now open to you, sir. Thank you.
Good afternoon all. At outset, let me thanks to the college and particularly Dr. Sylvia when she invited me. I was so excited to visit this college. Let me see. This is my second visit to the Madurai. So earlier I visited the Madurai Kamaraj University way back in 2014. Okay. So today I am going to be present on synthetic chlorophyll derivatives for energy harvesting. So by title you may understand that I am going to be present about the understanding of natural photosynthesis, how we can apply the principles associated with natural photosynthesis to design the materials for optoelectronic applications, particularly the energy harvesting. So I myself belongs to the CSIR in Institute of Chemical Technology. It is one of the 37 laboratories spread across the India. Okay. Let me see. It is. I hope most of the people they may not hear about the IACT. So this IACT is situated in heart of the city of Hyderabad, which is very close to the Secunderabad railway station, about 5 to 6 kilometers. And we have the it is a complete package of chemistry. You name it, any discipline of the chemistry, whether it is organic, inorganic or physical, analytical chemistry, the expertise is available in our institute. The beauty is that you can see that we have the catalysis division, lipids, chemical biology, discovery lab, genetic chemistry, diverse oriented synthetic laboratory, fine chemicals, agrochemicals, fluorochemicals, you name it, any branch of the chemistry, it is available in our institute. And the chemistry is the main core, and the peripherals wherever it is interacted with the biology, and we have the chemical biology people, and wherever we are interacting with the physicists, we have the physicists, and if you are interacting with the engineering people, we have the chemical engineers, mechanical engineers, electrical engineers, etc. So such a diversified chemical laboratory, and mostly focus on the scientific and industrial research. Of course, we are also doing the about 30-40% of academic research. See, it is we are equipped with the 450 registered PhD students along with the 200 project students where their MSc projects, MTech projects, M.Pharm.C projects, they used to come and stay 6 months, they complete their project and leave. So whoever interested in our institute for pursuing their projects in their respective degrees, or after the MSc or post-graduation also, if you are interested in the chemical related research, we welcome you our institute to pursue their PhDs. So for this, see, for example, the PhD is only one criteria. So if you clear the CSIR exam, you can always welcome and join whoever, whatever the discipline you like it. If you don't have CSIR examination also, we welcome you that you please follow our website iactindia.org. We almost each and every month we advertise the project assistants. So you can apply, and these days we are conducting the outstation people online interviews also. So we have created that facility also. Okay. Let me go to my presentation today. See, in G24 device, photovoltaic device, which is useful for the charging of a mobile. So what is the grade here? So it must be definitely a different technology what existing in today's silicon technology. So that is why our group is interested. So what are these technologies? Why this technology is superior than the existing technology? Okay. Then as time goes that another product is released in Dysol of Switzerland. This is a backpack integrated with the photovoltaic device. So this device is particularly useful when you are traveling or when you are going visiting to the remote place where there is no electricity. So we can by using this device you can charge your mobile, your laptop, etc. so that you are in touch with the other parts of the world. Okay. So as time goes that you can see that number of products are releasing. This is a simple lux meter where we can measure the intensity of the light, and a keyboard integrated with the photovoltaic device to run your laptop. And even recently they released a small device which is cost as on today it is a little bit expensive when compared to the silicon technologies. It is about 50 pounds, and by using this device you can charge your mobiles, laptop, etc. whatever the small devices which you are using day to day. Okay. So what is this one? See, if you look into the literature, silicon technology is not a new. In 1954, Bell Laboratories invented the silicon technology, and it came into the limelight in late 1970s and early 1980s. The reason is that time the people are interested to send their satellites into the space. So when you are sending the satellite in the space, how it is getting the electricity for running the satellite? Through these photovoltaic technologies. Okay. People know about the only silicon technology because the silicon technology as on day to day we are seeing everywhere. So once again, is a number of technologies, different technologies associated with this silicon based technologies. So like monocrystalline, polycrystalline, multicrystalline. And see, the crystalline means we have to grow the crystal of silicon in the macro size to apply these applications. It's not so easy. So another thing it is that where we can get the raw material. So silicon is nothing but the Si, the element present in the periodic table. So how we are producing? So just the raw material is silicon dioxide, that is the sand, to break the silicon and oxygen bond, covalent bond. So we have to give the large amount of energy. So during this process, a number of poisonous gases in the liberated. So people see, as we think that if we depend more on the silicon technologies, then we are protecting the environment. But if you see the very closely, it is not so. How we are making the devices, that is also very important. So then what will happen that next generation thin film technologies came into existence. Thin films means we can reduce the materials usage in the device fabrication. So in that way we can reduce the pollution. But again you see that thin films like cadmium telluride, gallium arsenic, etc. all are toxic elements. So the carcinogens, the most carcinogens elements in the periodic table is cadmium, telluride, arsenic. So if you depend on these technologies, then it's not, we are polluting. So we are the researchers, and we have to think about a step ahead than the ordinary person. So for that is the reason, the emerging technologies. See, these are the materials one can design in the laboratory and synthesize. If we can say that tomorrow that particular material is poisonous or toxic, we can redesign. So such kind of facilities are available in this emerging photovoltaic technologies, and which is not possible in previous technologies. And moreover, see, most of the raw materials is naturally abundant, and unfortunately it is not available in India. So we have to depend again the imports. But such kind of situation will not arise in case of emerging technologies. Okay. Let's see that. See, if you want to apply any materials for optoelectronic devices, my sincere suggestion to the youngsters, you please study the biological aspects about the natural photosynthesis, about the electron transport in mitochondria, and about the oxygen transport in hemoglobin and myoglobin. Then we can design the efficient materials. For example, if you look into the natural photosynthesis, what is the natural photosynthesis? Carbon dioxide and water in presence of light converted into the food materials. But By looking into the equation, it is very, very simple, but it is not so. It is highly complicated. So there must be a special mechanism required in the plants. That is the chlorophyll molecule, and in that chlorophyll molecule, the magnesium porphyrin is the main component. Okay. Then briefly, what is the mechanism? It is present in the natural photosynthesis, absorbs in the UV light, and the magnesium porphyrins absorb the light in the visible region and transfers the electrons to the neighboring molecules, and finally with the phenols. So as a result, what will happen? The charge separated species of porphyrins and phenols in milli to the nanoseconds is formed. So it is a huge charge separated lifetime. So if we can create such kind of molecules, we can address the hundreds of solutions to the optoelectronic materials. Okay. This is a simple energy electron transfer reactions associated with any organic molecules, and let's see that. Okay. Among the emerging technologies, a number of technologies are available. So today I am going to be discuss about the dye solar cells. So why I am stressing at the dye solar cells? All commercial products, what I showed in the initially, are based on the dye technologies, and it is totally different from the silicon technology. BSc laboratory also you can synthesize a majority of the molecules associated in this technology. So the device architecture is very, very simple. Okay, generally glass is the non-conducting. So if you want to make the glass is conducting, so we have to coat the fluorine doped tin oxide. And why it is only the fluorine doped tin oxide? Because if you put any layer on the glass, its transparency loses. But whereas if it is a FTO layer on the glass substrate, it will retain its transparency. So if you once lose the transparency, then the device efficiency is reduced. And of course, even in the silicon technology also same substrate people are using as on today. Okay, onto which nanocrystalline titanium dioxide is coated. It is a simple technique as a Dr. blade or spin coating, whatever. It is available even in some BSc laboratories also. And then synced at 500 degrees centigrade to get the molecule absorb the light. So coated on the surface. This is a photoanode, and opposite, of course, we need to have the photocathode too. Generally, it is the photocathode is platinum layered FTO glass substrate, and leave the two photocathode and photoanode a small space in between by inserting in a polyethylene sheet. Then after that you inject a electrolyte lithium iodide in some organic solvents. So what is the mechanism? When you shine the light, the chemical molecule absorb the photon and get excited, and the electron in the ground state get excited to the excited state and inject the electron into the PaO2 conduction band. From there the external load, and the oxidized dye get reduced by taking the electron from the redox couple. Okay, and this is a simple mechanism which is derived from the natural photosynthesis. So that is the reason. So if you understand the biological aspects very well in your BSc course or MSc course, then your life is cool in the optoelectronic materials and its application research oriented. Okay. Okay, this is the NREL chart, National Renewable Energy of the United States. Their task is that if any existing or new technologies invented in photovoltaics, so they will plot here, and as on today it is organic solar cells are at the bottom, and it is now picking up because it is invented in the early 1990s. Now just we are seeing the products in the market. Okay. How to characterize any photovoltaic device? So the characterization is similar in all technologies. So we need to have from the device how much voltage is producing and what is the light intensity. So from this we can calculate the efficiency of any device. Let's see that once again. We will go back to the dye solar cells. The dye molecule, because our institute is a chemistry institute, and we always prefer to design the efficient materials at low cost and durability. and then we always interact with the physicists and electronics and electrical engineering people to support for the device fabrication and evaluation. So initially the people started using the Ruthenian complexes, and with that, see, the IPC means the incident photon to current conversion, because see, you can see that an absorption spectrum in solution is different from the solid state. The reason is that in the solution the molecules are very free, so that is why we observe the very sharp absorption bands. And whereas in the solid state the molecules are very close to each other, and there are pi-pi interactions and van der Waals forces of attraction, hydrogen bond, etc. So that is the reason we always observe either blue shift or red shift to broad absorption. The IPC is nothing but any molecules in the solid state. So generally it is that in the ruthenium case it is the 500 to 600 or 650 nanometers absorption, and with these molecules it went to the device efficiency up to the 10 to 12%. Okay, and very recently by using the organic molecules it went up to the 14 to 15% device efficiency. So remember that because our day-to-day activity is the amorphous technology, amorphous silicon devices, and amorphous devices is about around 10% efficiency with the durability of 20 years, and which means that the new technologies already crossed the amorphous technology. Okay, then of course this technology has some advantages. See, whatever the technology we are developing, so it is relevant to our nation, which means that ours is a tropical country, and wherever it is, then from Kashmir to the Kanyakumari, we can expect to 8 to 10 hours sunlight in a day, and particularly if it is a summer, then we can expect more than 12 hours. So the reason is that the efficiency increases with the temperature, and which is exactly reverse to the amorphous technology. And it works in the diffusal light also. For example, and you are sitting under the light. If a mobile is integrated with this technology, and you just point it out towards the light, then it will be automatically recharged, and which is not efficiently recharged in case of amorphous technology, and less dependence of angle, because this technology you can just throw into the sunlight and where it absorbs the light and it will start working. And transparency windows, for example, and if this technology is completely commercialized and our windows is now the glasses, so we can replace with the glasses with this technology, which means there is no separate space required to install this technology. That is another added advantage. And color, of course, if you are using the internally householdings, so you can design whatever the color you like it, and less energy consumption, because there is no requirement to invest the hundreds of crore rupees on this technology. This is a small scale. If it is completely developed the technology, even our you can buy the materials from commercial source and sit at home and you can fabricate the device. That is the advantage of this technology. And as on today, the efficiency point of view, it is outperforms the amorphous technology. Okay. Then you may ask that what are the problems? Of course, every technology associated its own technological disadvantages. The main reason is that we are using the liquid electrolyte in estonitride solvent. So estonitride is highly volatile. So if you fabricate the device and throw it into the sunlight, after a couple of hours the organic solvent is evaporated, then it is dye the device. So one has to really look into the two aspects. One is that the sensitizer part, and the second one is the electrolyte part. So if we can address these two issues, then we can think about the commercialization of the technology. Okay. So as a whole, the research activities is the electrode materials, then semiconductor metal oxides, and dye molecule electrolyte. But my talk as today restricted to the dye molecules only, and of course our research group at our institute, we are addressing almost all aspects of the devices, right from the materials design, characterization, and device fabrication, and even the scale up of the materials also. Okay. So we cannot take the all the molecules, whatever the chemical molecules are there in the literature for the application of these devices. So each molecule has a certain characters it has to fulfill. First one is the broad absorption. See, if you see the solar emission spectrum from the right from the UV to the visible to the near IR region. So any molecule, if you can design such a huge absorption, then we can expect a better efficiency. But if you look into the literature, such kind of molecules are not available, and we have to really make it such kind of molecules. Then we can expect them the higher efficiency, like a 10%, 15% kind of thing. And the organic molecules must be easily be synthesizable. And another thing it is that it must be soluble in some solvent. Otherwise, if it is not soluble, then we have to adopt the chemical vapor deposition techniques. Then the technology, again, we have to invest the hundreds of crores. So to minimize all those things, let's start with some dye molecules. And our group at our institute, we are concentrating all aspects, whether it's a metal complex, organic molecules, natural pigments, etc. We developed more than 150 dyes, and very vigorously we are working for the last decade, out of which today I am presenting how our story got success in understanding the natural photosynthesis, apply those molecules for these kind of applications. Okay. Let's see that if you see the natural photosynthesis, the magnesium porphyrin is the main core. And what will be its absorption? Its absorption in the UV region and visible region. And when we initiated this kind of work in 2010, we started looking into the literature, but unfortunately it ended up with the less than 1% of efficiency device. So therefore it is only the academic research at that time we thought. And then let's see that I don't want to leave this research. Then we started looking into the synthetic chlorophyll derivatives, particularly for the zinc type of porphyrins. Because why we choosing the zinc, and it is abundantly available in the India. So we don't. If tomorrow we depends on this molecule for the technology, then we need not to get the imports. So but the efficiency is very, very low. So if we can push the absorption towards the red region, then we can think about it. Okay. So we need to have the, which means we have to remodify the molecules. So what are the positions, like beta pyrrole positions, A4. So this is a different technology, no need to remember and see that molecule only. Okay. So there is a one molecule reported in the 2000, that is a tetracarboxyporphyrin with 3.5% efficiency. Then it is a synthetic chlorophyll derivative, and when we did the DFT calculations, we found that the electron cloud is on the pyrrole molecules, not on the phenyl groups. Then at that time, so your faculty, Dr. Sylvia, joined the PhD in my group, and then I assigned this job to her, and I just asked to make the beta carboxy porphyrin. She struggled a lot. She spent more than 2 years time, and finally we got success, and you can see that the absorption is shifted towards the red region, and we thought that this is an excellent molecule. But when we applied to the device, we got 0% efficiency. Then we are that time we got the depression, and then we redesigned the molecule. Let's see that. Okay. Then we introduced some other molecules in the porphyrin case, and the absorption is further shifted towards the visible region. And you can see that now we are in the right direction, but we got only the less than 1% efficiency. So which means that we thought that yes, if we can really design the efficient molecules, then we can further push the efficiency of the device. So peripheral positions, and you can see that the absorption, particularly in the visible, near visible region, the extension coefficient is enhanced, and a beautiful IPC spectra we observed from 300 nanometers up to the 700 nanometers at the device efficiency of more than 5%. So we are in the right direction. So that is the reason, that is the research. We have to, if you got the negative result in the beginning, don't depress, and we have to think about it really. So where it went to the wrong, then accordingly we modified the molecules, and now we reach up to the 5% efficiency. But that is also not sufficient. We have to reach at least a double digit. Okay, then we change the design concept, and again here the natural photosynthesis phenomena we adopted. How that carotenes, porphyrins and phenols is a donor pi acceptor system. We adopted such kind of system, and the donor and porphyrin and the acceptor systems. So here what will happen, when an electron is transferred from the zinc porphyrin to the titanium dioxide conduction band, the hole is moved towards the donor. So as a result, what will happen, we can expect the long-lived charge-separated species, porphyrin molecules, and we got, but again here is, we end up with the 3% efficiency only. So while we are doing the photophysics, we understood that there is a chance of recombination with the electrons present in the AO2 conduction band with the oxidized dye molecule. So in the next, what we have done is that we introduce the long alkyl chains at the ortho position of the phenyl group. So by using this concept, what will happen, it will form the alkoxy groups is covered the porphyrin molecule, so that it will avoid the minimize the recombination. So by this, then we can expect the better efficiency. Then you can see that the absorption is also, the extension coefficient, particularly in the visible region, is enhanced. Okay, and then DFT calculation suggests that the HOMO on the donor and LUMO on the acceptor, then we can expect a charge separated species very efficiently in this kind of molecules. And you see that now the IPCE from 300 to the 900 nanometers. So this is the first kind of molecule, a single molecule showing such a broad absorption in the literature. So we proudly say that at the time, the CSR ISCT Institute and our director immediately said that he asked me to file the patent. It doesn't matter whether it is Indian or European patent. Then immediately we got the Indian patent, and you see that the efficiency of the device is more than 10%. Now we are in the right track. So this is the way we can design the molecules. But I did not discuss about the synthetic aspects of each and every molecule. So it is about 10 steps or 15 steps are involved in each of the molecules. But you can see that the end of the molecule, you see its properties. But initially about its solubility and then IPC spectra. If once these two fulfill, then automatically it will come the device efficiency. Then after that, what we have done is that about next point is durability. Okay, you reached the 10% efficiency. What about its durability? Then what we, after the made the devices, then we just throw it into the sunlight, and continuously each periodical time, like 10 hours or 20 hours, we measure the device efficiency, and even after the 1000 hours, and we got the initial efficiency. These are the accelerated tests, and 1000 hours is equivalent to the 2 years of its lifetime. Okay. Then after that, okay, these are the, again, how to, we are redesigning the molecules. Is it possible to push further the efficiency of the device beyond the double digit or not? And again, we did the different set of molecules, and you can see that now the IPCE we extended further up to the 950 nanometers. Now we understand about the logic behind that, the design concept, and now we are proudly saying that our institute we can synthesize and develop the broad absorption porphyrin based sensitizers. and the recent molecules, and it went up to the 10.5% efficiency. And now see why I am stressing this much. You see that ruthenium complexes in chemical catalog, for example in the Aldrich catalog, the price is about 1 gram price is about more than ₹1,00,000, and whereas our molecule is less than 2,000 rupees. So that is the beauty. And moreover, and ruthenium natural resources is not there in India. So we have to depend once again on the imports to avoid all those things. So these molecules are the very, very potential. So in coming 4 to 5 years, I can proudly say that you can see that the devices based on these kind of molecules. Okay, we are further redesign the molecules and see that whether it is we can further push the more than 11% or not. But we end up with the 10.5%. But now we stopped designing of new molecules when we presented this. See, we are only making the milligram scale. So the technology demands the multigram scale. So then we presented the work in front of the CSIR, and they sponsored a project just to scale up of the molecule. One of the porphyrin molecule we successfully scaled up to the 2 gram level. So again you can say that is a process development. So we have the not only the development of molecules at the academic level, and but also we can produce the molecules in multigram scale level. And another important aspect is that if you see the Aldrich catalog in the ruthenium complexes, that is made out of our ISCT technology. And even in the ruthenium complexes also we went up to the 10 gram scale level, and we transferred the technologies to the industry, and the industry people are selling the molecules to the Aldrich people. So it is since we are not completely in the academic, and we are understanding the academic research and try to translate the technology oriented. So this is the kind of the CSIR laboratory is working in a different manner when compared to the other academic institutes like IITs, NITs, central universities, etc. So as a nutshell, we started our journey in this porphyrin based sensitizer with 0% efficiency and end up with the 10.5% efficiency. So next another 5 to 10 minutes. Okay, then what is the reason, what is the speciality in this molecule showing the greater than 10% efficiency? And is a design concept, or what about its photophysical aspects? Because without understanding its photophysical aspects, it is not possible to further redesign, or if you want to go for the big panels, also not possible. Then what we have done is that, okay, we have taken the one of the molecules of porphyrin sensitizer, and we measured the first initially absorption in solution, and then in solid state, and absorbed on the TiO2. And you can see that when absorbed on TiO2, and the absorption is shifted towards the red region. But in solution it is a sharp bands, but in solids is a broad bands. And you can see that the emission spectra also in solution is a sharp, and the solid is shifted towards the red region. And whereas the emission on TiO2 is completely quenched. Okay, up to this the photophysics is what we expected. And let's see that it's really the excited state lifetime and transient absorption properties. And for this we have adapted the femtosecond laser, and first initially we done the excited state lifetimes. The molecule in the solution showing the 1.1 nanosecond is a typical any porphyrin excited state lifetime. Whereas in the thin film and on the absorbed on a TiO2, the lifetime is drastically reduced to 0.19 and 0.27. This is also the expected photophysics. Then what speciality is there? Why it is showing this kind of device architecture, molecular architecture showing the more than 10% efficiency? Okay. And we did the transient absorption studies. You can see that a solution and on thin films and on TiO2. See, particularly on TiO2, the band at the UV region is completely vanished, or partly almost more than 90% is vanished, which means that there must be an electron transfer from the porphyrin molecule to the TiO2 conduction band. And this is also not any new. Then we have done a complete kinetic study, and you can see that of course if you excite any molecule, first the electron goes to the singlet state, and then intersystem crossing happen, and you can get the even triple state also. And from singlet state you can see that the electron injection from singlet state to the TiO2 conduction band about 370 picoseconds, and from triple state to the TiO2 conduction band is about 450 or 500 picoseconds. See, here the beauty is that both the singlet and triplet states are contributing towards the efficiency of the device. It is there in ruthenium complex, so that is why showing at more than 10% double digit efficiency. But people are attempted the other metal complexes of all periodic table like osmium, iridium, palladium, copper, zinc, nickel, iron, but the efficiency is only 1%. The reason is that again ruthenium, the beauty of ruthenium complex, both the singlet and triplet states are contributing towards the efficiency of the device, and in our molecules also contributing both the singlet and triplet states for the energy conversion. Generally, see, if it is a singlet state, singlet quantum mills are high, means we can expect the better efficiency. But it doesn't matter here whether it is singlet quantum mills or triplet quantum mills, because both are contributing. So that is the reason. So this is the one of the rarest molecule, a pigment-based organic molecule showing such a kind of behavior. And for last 10 years we spent on this category, and this is one of the success story from our group. Of course, we have done even in the multigram scale synthesis and other pigment molecules like phthalocyanins, carols, etc. Okay. See, you can see that the charge generation is in 100 picoseconds and the charge recombination is 0.58 microseconds. So our target is that micro to the nanoseconds, because the natural chlorophyll charge separator species in sometimes in the nanoseconds also. So if we can design further redesign the molecules so that the charge separator species, if it is in the nanosecond level, then we can expect the 25% or 30% device efficiency. So this is the take-home message from my talk, that if you can develop any organic molecules whose charge separator species in the micro to the nanoseconds, then we can efficiently design the materials for optoelectronic applications. And see, we ourselves is not restricted this kind of molecule to the disolar cells, and recently we extended the work to the photocatalysis of hydrogen production. And another interesting thing it is that recently we did the photocatalysis of carbon dioxide, and this particular sensitizer exclusively ended up with the methanol. So that is another. So because of that story is totally different, so I am not included here. The next target is that now we are using the glass substrate, and it is a little bit heavy, and sometimes if it is fell down from your hand, means it will break. Then there is no point for this kind of technology, and we can replace the glass substrate with the plastic substrate. So that is a highly advantage, and we can roll these devices and keep it in our bag, traveling to the remote places, and we can use this technology. So our ultimate aim is that to change the substrate from glass to the plastic substrate, and with the device efficiency is 5% with the 5 years durability, because as on today we are successfully proved that the device efficiency absolutely there is no problem, and the durability we went up to the 2 years. If we can further improve the device durability up to the 4 years or 5 years, then we can think about the, at least in the small scale applications, replacement of silicon technology with this kind of technology. And I hope that in the coming next 5-6 years we can see more of these kind of products in the market for the small scale applications. Okay, these are the various technologies for VAT production, how much cost, because as on today you can see that about the 38 cents per VAT production in the silicon technology. Of course, this is the globe giving the subsidies to various levels, that is why as on today. But in case of our technology, it is about $1 per VAT. But If you go for the massive production of this technology, then definitely cost will reduce. And the important aspect is that there is no depending on the natural resources. We can design the molecule in the laboratory, and suppose tomorrow you feel that these potent molecules are also toxic to the nature, and we can redesign the molecules and to suit for the environmental claim. Okay, and I'm also serving to the journal Solar Energy as an associate editorship, and this is the first journal in the entire globe on solar energy. It started the journal in 1964, and I'm representing the Asia Pacific region. And whoever pursuing the research in solar energy, it doesn't matter whether it is a photovoltaics, and even we are inviting the manuscripts for the solar to thermal and solar to chemical, wherever the solar is there, and we are inviting the manuscript from others. And see, first I have to thanks to my students, because without our strength in the institute is the students. And we can see that so far 15 PhD students have been graduated from my group, and today's work is totally based on Dr. Sylvia and Dr. Vamshi and Dr. Suman. These three students work on today's my presentation. Of course, I have also a rich number of postdocs, and majority of the postdocs are well settled in India, like IOCL, ISAP, Trivandrum, and SECRI, and in various pharma companies also. And I'm very thankful to the funding for DST, CSIR, and MNRE. So DST has so generous when we started this work. So we got like Indo-UK program, we run about 9 years, and DST European Union about 3 years, and MNRE through TAPSON program of entire CSIR laboratories to be involved, and there I'm the national coordinator for this program. And we name it any disolar cell person across the globe, we have the collaboration with them, including the Professor Gretzel, Professor Richard Friend, Professor Durant, Professor Henry Snate, whoever the stalwarts, you name it in this technology. And DST has encouraged our group to collaborate with them. And thank you very much for your kind attention. And once again, I'm requesting to particularly the MSc students and whoever are interested in chemistry and chemistry related research, we are welcoming to CSIR ICT for various programs.
Thank you, sir, for the thought-provoking session. Thank you for providing opportunities in CSIR IICT Hyderabad and new technology on photovoltaics and dye-sensitized solar cells and its efficiency with advantages and disadvantages. Now the session is open for discussion and questions.
Thank you very much, Professor Giribabu. I think it's a wonderful talk. I just have one question, that because you have shown that you are having designed a molecule which couldn't do that, and yeah.
See, now we understood that the design of a broad absorption molecule is not difficult. See, how the natural photosynthesis was, like keratins, porphyrin, and phenols. And similarly, we designed the molecules, for example, phenothiazine, inertial molecule we have taken. Phenothiazine absorbs in the UV region, and porphyrin absorbs in the visible region, and we end up with the strong electron withdrawing groups, particularly thiophene, benzothiazole molecules. So, by introducing these electron withdrawing groups, the absorption is shifted towards the red region. That is the one reason. And another reason is that, let me see, we introduced the two triple bonds in between the donor and acceptor. These triple bonds shift the absorption towards the red region. And the beauty is that, of course, we have some luck also. Luck is both the singlet and triplet levels contributing towards the efficiency of the device. In general, only the singlet state contributed towards the efficiency. That happened first in the ruthenium complexes, and after this our molecules.
Thank you very much.
Thank you for your valuable presentation. Your designed molecule has highly efficiency, 10%. First of all, we calculated the quantum computational for theoretically calculated spectrum. It covers broad range of spectrum. Your molecule also covers broad range of spectrum. The theoretical spectrum is matched with calculated experimental spectrum.
See, theoretical spectra you can get only about its absorption range and its homo-lumo levels.
Okay.
Because LUMO you can have to see that whether it is compatible with the TO2 conduction band or not. Only you can get the information to that extent only. But after that, what is its recombination percentage? Because see, when IPC is more than 80% means what does it matter? When 100 photons absorbs, 80 electrons are injecting into the TO2 conduction band. Out of 80 electrons, only few electrons are contributing towards the efficiency of the device. Rest of the electrons, where it is going? To the recombination of oxidized dye with the electrons in TO2 conduction band. So we minimize it there. So that is why that more number of electrons are contributing towards the efficiency. Okay. So these kind of information you will not, it's not possible theoretically. So we have to really do the photophysics in depth, then only you can understand.
Okay. Sir, another question is, UV and fluorescent spectrum, the band is near NIR region. Similar in case of emission in UV. What is the reason?
Sorry, I didn't understand.
Overlapping UV.
No, it is not overlapping. See, in solution, in general, it is a short piece. But in thin films or solid state, it is a broad band. Why? Because of pi-pi interactions, hydrogen bonding, or van der Waals process, etc. Okay. And similarly, the emission is also shifted towards the red region and the broad. And whereas in case of when absorbed on TO2, the emission is quenched. Why it is quenched? Because electron is injecting towards the TO2 conduction band.
Thank you, sir.
So thank you for the presentation. I'm just curious to know, like, what is the lifetime of these dye-sensitized solar cells, and how do we compare it with the perovskite-based ones? And the second question is, I'm just curious to know, we have synthetic rubber, we have synthetic cotton. Is it possible to have synthetic chlorophyll or such similar molecules that we can use for these applications?
See, perovskites. Perovskites is the fancy efficiency numbers you are seeing.
Yes.
As a single device, it went up to the 25%.
Yes.
And multi-junction devices, it went up to 28%. And low light conditions, it went up to the 42%.
Okay.
Here, the main drawback is lead. Lead is again the toxic material.
Okay.
So unless if you can replace the lead with some eco-friendly metal like copper, zinc, germanium, etc. And even tin also went up to the 18-19%, but unstable.
Okay.
So if you can replace the lead, then only you can think about the commercialization, technology point of view. That is the one thing. Yes, your cellulose, cotton fibers, all those things. See, now I did not cover the electrode materials. Electrode materials is, as on today, people are using the platinum, which is the expensive. That might be the one of the reason the device cost is about $1. So if you can replace the platinum with the carbon paste or your cellulose, you can get the carbon nanotubes out of it, synthesized from it, and we can use as a counter electrode. Of course, people have started using, and with using the carbon nanotubes, near 8 to 9% efficiency reported in the literature.
Okay. Thank you. And one more question, what happens to the solar cells after use? Like we have battery recycling units. Do we have any such for solar cells also after usage?
This kind of technology or silicon technology?
Both.
See, silicon technology hardly massively is coming since last 10 years.
Yes.
Generally, the supplier will give the efficiency lifetime of up to 20 years or 25 years.
Okay.
And now 10 years already gone. And the next 10 years we have to identify how to purify the silicon and then reutilize it. Now the intense research is started on silicon technology.
Okay.
And for this kind of technology, see, all are biocompatible. For example, porphyrin you take it, it's a synthetic chlorophyll, derived from the natural chlorophyll, and it is a biodegradable. And even our TiO2 is also biodegradable. So no toxic element is present in this technology, and moreover, majority of the material is biodegradable. And if you want to think about the recycle really, then if once the technology commercialized completely, then we have to think about it.
Thank you. Thank you, sir. Now I invite Dr. V. Sridevi, Associate Professor and Head Department of Chemistry, to honor Dr. L. Giribabu with a small memento. Thank you, sir. Thank you, ma'am. Now let us leave for lunch break. Lunch is served at GJ Auditorium. I request the participants to get back for the technical session in the same venue by 2:50 p.m. sharply, as we are running short of time.